Okay, so welcome back. So in the very beginning of my talk, I showed you how to get bone age assessment solved as a regression problem where you supplied a lot of images and you're trying to predict the label that's available to you in a CSV file. Correct? So let me show you some of the tools that I use to build these. This is a full script that I've written. I'll share this script later after this session. And you guys can play with it on your own and so on. I'll show you basically what the script runs like. And then what you can do is maybe collect in groups to talk to each other and try and reproduce it yourself. Try and see if you can do a simple bone age modeling yourself. I have created a tiny RSNA data set. I think only 50 images. The entire data set is huge. It's 10 gigs. So let's not play with 10 gigs right now. If you can get it to work with a smaller image set of, these are very large images. These are X-rays on the order of 2000 by 2000 pixels. So these are not small images. So the images are very heavy. So I created a tiny RSNA data set, which sort of allows you to get the code up and running. So the focus of this is, the focus of this is going to be to get your code going so that you make sure that you have a code. If you can run it with 50 images, you can run it with 12,000 images. Okay, then it's just a matter of having a more powerful machine on which you can run stuff. So let me see if I can find. I want to show you what the data set is. Okay. So I hope you can see that. So this zip file, I've placed it at this URL. So let me know if you can't access it from this URL. I have to allow access from Google Drive. And is that by request or to allow access? Okay, let me try doing that.
But can you make it globally readable or will you have to reply to 30 emails?
Yeah, I don't want to do 30 emails. I'll try and do one. What do I have to do to make it globally available? Oh wow, I got huge numbers. I'm already flooded. Oh, all right. Okay. I thought I'd done that. Apparently not. Actually, I'll do this in a minute. Why don't I first? You guys can get started on writing the code and then I'll share that. I'll make it shareable. Please don't send me any more emails. I'll make that link available. Anyway. Okay, so let's talk about the base. I'll move into the tiny data set. So it's a zip file. You have to unzip it, load it into your Google Drive. It takes a couple of minutes, not entirely small, so it takes a couple of minutes. And then you can use your code to access it. Let's show you what the data set looks like. Oops. Okay, so there's a bunch of images in there. They're of PNG format. You can take a look at any one of them. 1380. So that's what an image looks like. Okay, it's an image of a hand of the type that I showed you. If you want some information, you can see it's 1500 by 2000 pixels. So it's a pretty big file. Neural networks won't work with that big a file. They typically work with something on the order of 256, 224. Typical networks, we will use an ResNet network. How many people know what I'm talking about? Convolutional neural networks. Most of you know. I'll give you a 2-minute overview of what a convolutional neural network is. So basically, what a convolutional net does, it takes in an image. Remember, I talked to you about images as being arrays of pixels, right? So when you pass that array of pixels into an input layer of neurons, it will pass it down through successive layers. That's just a cartoon of how, layers upon layers of neurons are. And then finally, there'll be one output neurons. All of these guys will connect to it. That's called a fully connected layer. And the output of this neuron is the probability that you're looking for it to belong to a particular class. Or if you have a regression problem, then this is the regression output that you are interested in. Okay, so this we're going to treat as a regression output. We're going to be interested in a regression output. Now, convolutional neural network is a very special kind of neural network which has the following feature. It takes your image and it takes a kernel. A kernel is a specified weight matrix. Okay, so there are values over here. Okay, think of this as a weight matrix. That weight matrix does a dot product of here. Dot product with this. It's not the dot product, it's a product. It's a convolutional product. Okay, so take this, place it over here, multiply element to element, and take an average. Slide over the kernel to the next one, get the next set of values. Slide. Basically, applying kernel onto the image results in a new image. That new image is the convolution of the kernel and the, I don't want to use I. So it's a sliding window of weights that you apply and slide over your image to produce an output. Okay, that output can then be passed into functions like ReLU or something. So those outputs can be massaged in particular ways. I don't want to get into the architecture very much, but essentially there's a couple of convolutional layers, then some normalizations, couple of convolution layers, some normalizations, and so on and so on. Okay, so you can read up about all this. I don't want to get in the math of how this thing works, except to say that essentially what a convolutional network does is to apply compositions of convolutions. You have a convolution, you do another convolution, you do another convolution. So these are compositions of convolutions, which is essentially, and with certain renormalizations that are going on in this. Okay, so maybe later I'll show you a view of what VGG16 looks like. Okay, because there are many layers, that's why it's called a deep network. That's all that is there to know. Now, are you going to design a network from scratch? No. Typically, no. That's essentially what this is. So these networks have been developed. Some of the old networks that were developed had fewer layers, AlexNet and so on. Then they came the VGG level networks. Then came ResNets. And then now there's a zoo of networks. So typically, when one wants to use it for applications, one uses the standard networks that are available. So ResNet 18 and ResNet ResNet 18 and ResNet 50 are very good networks. By default, the first model of choice is to use the ResNet 18. If you get more deeper into this question of what a residual network is, how does it differ from some of the older models, what's new in the newer models, you can come and talk to me afterwards about that. Okay? My goal over here is to be able to get you up and running so that you can do a basic script to run a regression network and start to see if the error is something that's reasonable or not. Okay. All right. So that's essentially what I want to say about this thing. Now, let me say a few words about training the network. So remember last time I said, once you have a network, think of it as an input-output transfer function. And the output is compared to the ground truth. Okay? You compare this ground truth and you change the weights in the network. based on how much the ground truth differs from the output. So the loss function is, say, some function of the output and the ground truth. Okay? Typically, you can consider all sorts of functions. I mean, typically a quadratic square loss, mean squared loss would be a reasonable error if you're looking for a regression problem, right? All of you know this from linear regression, so I don't want to belabor it. The standard Euclidean norm. Take all the bits here and take all the bits here. Take all the values here and take all the values here. Find the square distance and let that be your regression function. You can choose other regression functions. Okay, like for example, L1 loss would be another regression function that's often used. In fact, for this problem, one would recommend using an MAD loss, so L1 loss rather than L2 loss. But you don't have to worry about those details. Those details are best done when you start specializing into this. Typically, MSE loss is a standard function that's available to you in PyTorch. So you can go ahead and use that. What you're doing is gradient descent. So gradient descent means you've got this loss landscape, some surface, and you're trying to find some local minima. This is not a global minima. This is some local minima. And so how do you find some local minima? Actually, there are many. There are many local minimas, all of which will suffice for your problem. So your goal is to find one of them and sit in that. What I mean by that is you want to lower the loss until it finds a suitable minima where the generalization is reasonable. So what would you do? Well, first of all, your training error, you want it to come down as much as you can. Okay? But training loss, when I say training loss, it's the loss on the training data set. You want to fractionate your data set into training, validation, and test. How many say training and validation? And how many would recommend training and test? What's the difference? You know enough machine learning by now. Huh? Loudly. What's the difference? Okay. Yeah. So would you do 2 data sets split or 3 data sets split? That's the point. How do you decide? Yeah. Yeah, you've said exactly the same thing that he said. My question is, how do you decide whether you want to do a 2-way split between test and train or a 3-way split between test, train, and validation? I'm not talking about cross-validation. It's all supervised because you have an output, a target output you have it. Yeah. Okay. Validation data satisfies that as well. You never show it except to validate, right? Training is not done on the validation side.
So there is a feedback which is going on from validation test to the training data, because of which bias can come, and the information leak, to avoid the information leakage.
That is an answer whether you should use a 2-way split or a 3-way split. The validation data is used to fine tune. It's to select amongst models that are trained. So the validation data set will be used while training. Yes, because you want to get as low a validation score as possible. That's when you know you've got a good model, right? All of you have said the same thing, but nobody's answering whether you should do a 2-way split or a 3-way split. Yeah. Who's that saying that? Yeah. What does Benz? Yeah, that's correct. So ideally, you would like to use the validation data to score your test models or training models, and then use a separate test data to make a prediction score. That is the generalization score of your model. In practice, however, if you do not have enough data, you cannot afford a 3-way split, then whatever you get on your validation data, even though validation data is used to train the data, Whatever is on the left, whatever is your validation score, you use that as your proxy for generalization error. And that's when resampling techniques like 5-4 cross validation come into play, because you can swap around the validation sets and then get a better better sense of what the generalization score is. Is this clear? If not, you can discuss with me later. Basically, what we are doing, our goal is not to get into those details. Our goal is to decide, is training error coming down? What is our acceptable validation loss? Okay, so that we can check then whether our predictions are close enough to the ground truth. That's what our goal is going to be. Okay, so your loss landscape will be constructed from this loss, and your weights will be changed. Now, another thing that I want to describe to you is when you go through this gradient descent doesn't mean that on every change, on every step. So let me say what a step is. A step is I'm at this position in terms of weight space. With respect to weights, I'm there on the loss landscape. If I move, I will move. Why? I will move because I'll have computed the loss here, and that determines for me the gradient of the direction in which I should move. I move along, and then I can keep doing it. Now, there's a couple of ways to do it, right? You could take the entire data set that you have and compute and make a step based on the entire data set. You compute the loss with respect to all the points. You take one, find the loss, take another, find the loss, take another image, find the loss, take every point in the data set, find the loss, add up the loss, that's your total loss. Use gradient descent based on that entire batch. One way to do it. Can you come up with 2 more ways to do it? You can take it in batches, right? So you take one full batch, compute the loss, make a step based on that, and so on and so forth. You can do batch-wise loss and then make steps. Or you can do a third way, which is you take one single point arbitrarily selected, jump. Right? So you can do it point by point, you can jump point by point. Data by data as you get answers, jump. You can take batch by batch and jump, or you can take the entire data set and then jump. Okay, these are different forms of gradient descent. They go by various names like stochastic gradient descent and so on. And you can play around with those. That's up to you. So batch size is going to be one of the hyperparameters, one of the tunable parameters in your model. Okay. All right. So this is how basically training is going to work for us. Now let's take a look at the label file. So this image file has a certain name. That name is 1380.png. So that's the study code of this image. Now I also have a CSV file. Let's take a look at this CSV file. So the very first column, it's a CSV file, comma separated. The very first column is the ID. So 1380.png will be the corresponding image. So the .png is removed and only the ID is kept. What kind of variable is 1380? Is it numerical or categorical, or what kind of variable is it? Is it a string? File name would be a string. So 1380, what is it? A string. Okay. If I store it in a CSV file, is it a string? Okay. So it depends on how you read in this file, right? And that is handled by what? So everybody knows about a pandas data frame. Who doesn't know what a pandas data frame is? Oh, most people don't know. Okay. So we will learn about pandas. Okay. CSV files are read by, as you would read Excel files, right? So you would have to have a facility to read a file in. I'll show you all of this in a minute, right? If you're lost, if you're feeling lost, I'll show you in a minute how easy it is to do all these things. We shall go to ChatGPT to find out. So actually, we could try that. Why don't I just show you how to do it? So there are 3 co-pilots available. Typically, one of them is ChatGPT itself. The other is GitHub Copilot. And the third one I recently heard of, but I haven't used it myself, is GitHub Copilot Chat. Apparently GitHub Copilot Chat is very powerful. ChatGPT, of course, is free. So this is my ChatGPT framework. I assume you all know how to use ChatGPT, right? Who has not used ChatGPT in this room? No, well, you should learn it. There's lots of people who used it. Time to switch. So my prompt is up here. If anyone can't read it, please let me know. You are a Python developer. Show me how to read a CSV file into a pandas data frame. Show me, it won't work. Will work? Oh, it doesn't matter. It doesn't care if I make mistakes, but it makes mistakes, so you have to be careful. Okay, see, you got some very helpful tips here. That line says pip install pandas. All of you recognize that. If you don't have a pandas installed, well, as a pip package, you have to install it. It actually gives you a nice little file. Remember, our file is very close to this, Bonage, ID, and mail or not. It's got 3. Import pandas as PD. File path is the point to the file. And this is the key definition you want. PD.read CSV file path, and you put it into a data frame. If you don't know what a data frame is, you can ask it. What is a pandas data frame? And it'll tell you all sorts of stuff, right? So basically, it's a data frame is a structure that you use to interact with files that are stored in Excel or CSV type. Okay, so you can go through reading all this, right? So all of so now that makes my life easier. I just have to tell you how these things are constructed, and then you guys can take over. So that's what I'll do. What I'll show you is how this overall structure is constructed. I'll point out some of the salient features or what is it that you need to get done. And then you can interact with ChatGPT and try to get it done. Does that make sense? Okay, so those are my imports. I showed you my imports earlier as well. What's the first step that I have to carry out in order to create a PyTorch model? If you recall from my previous lecture. Well, the first step is to create a class that is inherited from the PyTorch dataset class. And I'm going to call this a custom dataset class. If you remember, that has to have a constructor. So it has to have an init function. The init dunder function has to be implemented. In this case, I'm going to pass it an image directory because that's where my images are stored, a CSV path because that's where my CSV file is stored, which contains the labels. So I have my images and I have my labels, and I have to import both of those into my class. So, self.data, that's your pandas read CSV image directory that points to the image directory. I'll tell you in a minute what transform is and how you should use transform. You have to define the length dunder function. Length dunder function actually tells you how many data points there are in that data set, right? Now it can get a little bit complicated if the number of images do not match the number of rows in your data file. That's where data warehousing comes in. So you can make this a little bit more complicated. I made life things easier and I made the tiny RSNA nice and sanitary. So everything is okay. I'm disconnected. Okay, I'm not going to connect a runtime. So you guys all know about runtimes, right? Right, you can connect a GPU to runtime, or you can run it off of CPU. CPU will be slower, GPU will be faster. Google provides you a GPU, might as well use it. Okay. The one annoying bit is that every time the runtime disconnects, I lose access to my data. So I have to reload my data. which is why I didn't want to, well, so which is why I created a tiny data. So that once you know, it's always a good idea to batch try things out, right? Working with 10 GBs and something goes wrong, you don't know what is going on. Try it with 5. What's wrong with 5 images? The code will still run, right? So you should always try things out with fewer images so that you know exactly what you're doing. Everything is faster with 5 images, right? You'll just debug faster, you can run codes faster, everything will be faster. And then what's the difference between 5 and 5,000? Nothing. Once your code is right, it's sanitary, it will work for 5,000. Okay. What kinds of errors could arise? The kinds of errors that could arise is there's a mismatch between the data file, the labels file, and the number of images. Maybe maybe the image failed for some reason. I mean, your neural network failed for some reason. It didn't produce the right output, and it went quiet. It quietly did not give you the right output, but it did not throw an exception, so you don't know about it. Something has gone wrong. You are left to debug it. Those are the questions that come up in active practice. Hopefully that will not happen here today because everything is so straightforward. Yes. Well, yeah. I'm doing that because I want to inherit from this class data set. It already has a lot of the things. Otherwise, I would have to implement my own gradient functions in the computational graph. So this dataset class is provided by. This has to be written down. The format is this. One has to tailor it for the problem at hand. So let me show you. Let me answer that in a different way. Write a simple. You are a PyTorch developer. Write a simple custom dataset class to load data. Let's see what it shows us. This is what it shows up. Yes, and I modify it to what I want for my code and how it should process my code. Yeah, so that's all you need to do. This is boilerplate code. So you can just cut and paste boilerplate code, but you have to then modify it, adapt it to what you need to do. Like I have to know that I'm importing in a PNG image, not a JPEG image. So I need to make sure that the code is right for that. So yeah, okay. So the next thing that you have to do is you have to implement the get item dunder function. Okay, that takes in an IDX. So this is an index into your data set. You got a data set. Your data set was images and labels, and each one of them, the image is corresponding to a label, right? You have a locator. You have an IDX index position for which image corresponding label pair you're at. Does that make sense? Any questions? So you take in IDX, and that brings you that index. So you can get the image name, the age, and the sex. Those are the 3 fields in your pandas data frame. Remember, the CSV file has been loaded into a data frame. The data frame is just think of it as an Excel. You use this function called iLoc, which is an indexed locator, into that Excel file, pointed to by IDX, which is what the argument of this function is. Then you calculate the image path, which is this function says, take the image name, which is just that string, and you add PNG to it. Okay, so if you don't follow this syntax, don't worry. There's always ChatGPT can help you with that as well. How do I convert, etc., right? So then I open the image and I'm converting to RGB format. Remember to do this. Some images are grayscale. The images in RSNA are grayscale. The ResNet works with 3 channels, assuming your images are RGB. So I am pseudo converting an image, which is a grayscale image, into an RGB image. Okay, that just says take the first channel and duplicate it 3 times to make a 3-channel stack. And that's an RGB image. Okay, that's a pseudo conversion, but this convert.rgb function will allow you to do that. Age label, you have to, so all of these things are torch tensors. You want to convert the age into a float and torch. You can convert it into an int if you like, if you think that only integer variables are allowed. In this case, I converted it to a float. So 120 will be 120.0, right? It doesn't have to be. I converted it to float because I thought that might be useful when calculating loss. It doesn't have to, right? Okay, now image dot transform. This is a very important function. If self dot transform, then do self transform on the image. Okay, this is part of the get item itself. You are allowing for the image to be transformed as you are importing it into your data set. Why do I have to do that? Because I have to resize images. I have to resize images. Remember that neural networks will work only with 224 to 24. I'm doing a cheat of a conversion here. I am taking the image and I'm just importing it, resizing it to 294. So remember, I showed you that image earlier. Can anyone tell me what caveat there might be in doing this? It seems easy enough and you would just do it, but you'll run into trouble. Why? So we just did it when we first did it. And then we realized a couple of days later that, oops, that's not what we should have done. Can anyone guess why we went wrong? You don't want to import your image just like that and resize it to 224. Aspect ratio will be destroyed, right? So you want to retain aspect ratio, in which case you pad appropriately the right dimension. So that's one of the exercises. You can think of how would you pad your images and then resize so that the aspect ratio isn't changed. You just get a black board. Okay? So I'm not going to do that right now. If the aspect ratio is distorted, I'm going to let it slide for this basic code. I want to make sure that this code runs. Then I can add all of these embellishments. Okay. So did I create something? Yes, here it is. So that's the class. I set my CSV path. Notice that if you just load it up from Google Drive, that the path is /content, and then the data set where you've unpacked, and the CSV or the data set file. And I'm going to put in a few transforms. The transforms are composed like transforms.resize. Transforms is a package which allows you to transform to 224 to 24. That's the input size of the ResNet network that I have. So every network has its own input size. And in fact, there's a bit of nuance to it, which means that the event size can be variable and so on. But let's not worry about that nuance right away. Just typical network input image size is what we are working with right now. Okay, and then I have to transforms.toTensor. This toTensor is important because, okay, I can resize it, but what is it? I mean, it's some sort of image that different packages can have different representations of the image. So I need to transform it to a PyTorch by using this to a PyTorch format using this toTensor format. This toTensor is something you have to look out for. Sometimes you miss that. If you miss that, things are bad. Okay, I mean, it might work or may not work. No, but whatever answer you get will be kind of spooky. And there's a nuance around this also. It's probably a little too early to go around discussing that. Let's talk a little bit about. So this is my transform. Now these two lines are the workhorse, right? That custom data set I just created, that class, I pass it the right parameters and create an X-ray data set. And from that, I can then create an X-ray data loader. So a batch size of 4, data loader, passing in the data set. This data set passed to a data loader to give me an X-ray data. I'm done as far as my data loading is done. Okay, now you can write your own little code to print out a batch of 4 images along with their labels to see whether the data was read in correctly. This is just some housekeeping I do before. See, I don't recognize bones. My clinicians will know bones. Clinician collaborators will know bones. Oh, wrong image, something like that. It can't be that this is a young child. You got the label wrong. But I can't do it. So I put in a lot of debug functions to make sure that my data loading has occurred correctly. Lots of things can go wrong here. And so this is a good debugging function. Okay, so I loaded up some images. I saw that the ID was 1417, age is 162. So what I do then, what I do is I go look up the ID 1417.png file. I open it to see that this image is exactly the same. Then I go to the CSV file and make sure that 1417 had 162 next to it. So those are all debug functions. Just a sanity check to make sure that this code is all right. You can see that the aspect ratio is distorted. You can almost guess it. If I don't know if you can see it in this image, but I've stared at these things long enough to know this is bad aspect ratio, and this one also. So the aspect ratio is something that you can worry about as a second step. Okay, now let's talk about defining the ResNet regression. So in inheriting from Menon module, I showed you that last time. Again, there is an init that goes into it. I'll show you the essential stuff. So number of features, this last line, what we are doing is this ResNet comes with a certain number of output units. We have to remove that set of output units and place how many units? 1. It's a regression problem. I wipe out the last layer and place 1 unit, okay? And enjoy finding out how to do that. Open ChatGPT and ask it how it does that. After a couple of cycles of going through it, you'll be able to figure out that the last layer in the ResNet. So this is actually self.resnet.fc. Can you tell me why? Why does this line say self.resnet.fc equals a linear layer, a fully connected linear layer with number of features to number of outputs? Number of outputs will be 1 somewhere. Here it is. Number of outputs is 1. I've created a model with this class with number of inputs. Number of outputs. So this is actually saying the last layer is called FC, fully connected, right? So it's a good exercise to try and figure out how these names are. I mean, I can always tell it to you, but it's good for you to figure it out on your own. You can always ask ChatGPT to show you, or you can actually, you don't have to go to ChatGPT. Inside Python code, you can ask it to describe the entire network for you. And then you will see what the last layer is called. There's a name attached to it. That name is FC. So you can remove, you can change that layer, wipe that layer, rewrite a new linearly connected layer. Does everyone get what I'm saying? The output number of layers is output number of outputs in the final layer is fixed. You wipe it and you place only 1 neural network and connect everything to it. 1 neuron, connect everything to it. Okay? Let me just draw it real quick. So you've got a bunch of layers. There's a certain number of outputs in the standard ResNet. You clean it up, place 1 unit and connect everything in the previous layer to it. That's what you have to do for transfer learning. Now there's a nuance around this as well. You can freeze the weights of the previous layers and only allow these weights to change. That's one way to do things. Why would you want to do this? What could be a case setting where all the weights from here to here are frozen, which means during the gradient descent process, they cannot change. And you allow only for these weights to change. Why would you want to do that? Say you have trained this network on ImageNet. ImageNet is a large data set with all sorts of real world images. And you say that my images are not part of the ImageNet data set, but if a network has been trained to see lots of human human recognizable images, and my data set is of particular type, like it's a data set of different kinds of pen caps, right? So if a network has seen tables and chairs and birds and airplanes and so on, then recognizing pen caps is just a little bit more. So in that sense, you don't change all of the weights, you allow only these weights to change. There's another trick that one often uses, which is to allow everything to change. You say, oh, I don't know whether freezing everything will work or not. I will allow these weights to change as any of the other weights to change, but I will change the rate. I will allow these weights to change 20 times faster than all of the others, which means essentially you're allowing for the later layers. Okay, so those are some of the tricks that people use. or you can start with a naive network. I don't know any weight, let it be naive, arbitrarily initialized, and then I'll train the whole thing from scratch. Okay, so those are all things you can play with. All right, moving on. So I've created a little model with this class and number of outputs. I've kept it 1 because it's a regression. Okay, then final steps. I showed you this last time, so I will go over this quickly. Criterion, learning rate, optimizer. These are sort of the hyperparameters of your learning thing. I need to have a criteria. What criteria should I use is the loss function. So MSE loss could be a typical loss function that I use. Learning rate, well, you get to learn by practice what a learning rate should be. But typical learning rates, a good thing to start with is 0.01 or 0.001. Okay? Most machine learning algorithms, most deep learning with CNNs will use 10 to the -3 to begin. Okay? There are ways in which you can find an optimal learning rate and so on. Those are somewhat advanced topics, so we'll not go into that. Just try 0.01 and 0.001. Optimizer, we are taking Adam. Adam is a good optimizer. There's some SGDM and Adam are typical optimizers. There's also one Adam prop that people use. Between these three, those are the standard optimizers. That's it's called, and this is the training model. So let's look at the training model class. Obviously, the model has to be passed, the train loader has to be passed, the criterion, optimizer, and the number of epochs. Remember, I said the epoch. One epoch is complete when when the entire data set has been seen. That's one epoch. You could see it in batches. You could see it in one go. So if it's many batches, you're passing through the entire data set piecemeal. Okay. So batches and epochs. Epochs is one pass through the entire data set. So number of epochs, you can keep it 2, 5, small numbers so that you make sure that things are running. When you actually want to get to high epochs, when you're confident in your code is working and you want to lower your loss as far as it'll go, then you typically run high epochs. That's more production code. Okay, you pick out a batch, then you pick out the images, targets, IDs. Those are 3 fields in your pandas data frame. You enumerate over the train loader. That means you go over the train loader one by in sequence, which will give you images and targets. You pass them to the right device, because if you want to use GPUs, you want to move them to GPUs. If the default is CPUs, you zero grad the optimizer, then pass the image through the model, get an output, computer loss backwards. That means pass the information of the loss back into the network, step the optimizer, which means change the weights based on the gradients computed. And then this is just some boilerplate that allows you to print stuff as you go along. How many batches are completed, how many epochs have completed, what's the running training loss, and so on. So, I had run this a lot. Okay. You can see, I'm already at epoch 22. So let's start early. Oh wait, it must have rolled over. Okay, epoch 22 of 50, the loss was such and such. Average loss, then average loss is decreasing. It's come down to 2058 from 2874 in a sequence of steps over 20 epochs. Okay. I mean, almost surely I would never run this 50 epochs to begin with. I would run only 10 epochs at the most. But the moment it passed through the network, the loss goes, right? My loss was just initialized to 0, but when I computed the loss in my first pass, it went up. Well, it's just an initialization. I could set it to 5,000. It'll come down. It's just an initial number. I mean, it's a cumulative loss, so I set it to 0. And as it went through the epoch, it started picking up loss, so it went up. I want the training loss to come down as much as it can. Typically, with deep learning networks of this size, of the ones modern networks are, training loss will come down dramatically, 0.01, 0.02. It'll come down to very low values. Loss is the cumulative loss on all in one epoch. It will be the difference that you compute between these 2 points on everything in the data set. So if I compute, so if I get a prediction of 123 on an image that's 120, my loss for that, my error is 3, I square it, I add it up for all the points in the batch, in the entire training data set, take the square root, that's my MSE loss. I want to, if it is to come down as low as possible, then, so typically training set can come down because, in principle, you can predict everything in the training data set, but it won't generalize. For this exercise, actually 10 was quite good. See, the loss keeps coming down, and after a while it tapers off. And then your gain in the loss is not that much. What you're looking for is the validation loss. The validation loss should come down, and then when it tapers off, then you can't get any more gains. So 10 was actually quite good. After a point, this, the increment, the slight changes in the loss that started occurring didn't really add much. And then I have a finals function that says, okay, let me test this. So I'll let you write that on your. Okay? It pretty much follows the same same principles that we had included, except that when I'm calculating the output, now I don't need to do grad. So I will torch no grad, because when you're just pushing out the model, you don't need to keep the track of the gradients. The gradients were used for training and changing the weights. Now you're just passing your batch through and seeing what the output is. So you use torch no grad for that. Okay, so why don't you start writing, and if I can change the file permissions. Okay, I think I've changed the permissions. I hope you can download it now. Please try it and let me know. Save. And then import it from Google Drive. So those are the codes I've shown here. If data is in a local machine, use that grayed out, greened out codes. If it is stored in your Google Drive, you've uploaded to Google Drive, then you can use that kind of command. If it's on your local machine, use this. If it's on your Google Drive, you've already uploaded to Google Drive. I assume you know how to upload it to Google Drive. It's a zip file. Then you can use that. I would encourage you to get in some groups of 2 or 3 and work on it together. Pair program yourselves. I can volunteer 3 of my grad students to help you. Sandra, Shreya, and so much. Will you guys show yourselves, please? If you run into questions you want to ask, So one other trick is if you're trying to debug something and you're running into an error, right? You can cut and paste in your entire code of that class and the error message in ChatGPT, and it can help you debug it. It will give you helpful answers as to why you went wrong. This idea of prompt engineering, there's a lot of good videos on how to write effective prompts. This YouTuber Arjun Codes has a good set of videos on ChatGPT and prompt engineering suggestions. This is on YouTube. This channel on YouTube has lots of good information on ChatGPT, at least a little bit. It helps a lot. And if you want to learn more about what F strings are and things like that.